Okay, this is practice test 4B, and it says a report on 60 Minutes stated that the average person spends at least $800 on a vacation. Well, right there is our null hypothesis, and what we would say is that mu is greater than or equal to $800. And that would make our alternate hypothesis that mu is less than 800. Now let me get rid of this here a second. There we go. That should pretty much do it. And then again, the alternate hypothesis is that mu is less than 800. So let's go ahead and do the problem here. He spends, you sample 24 people, that's your N. Average vacation cost of $750, that's your X bar with a standard deviation of $25. And it says test at an alpha level of 0.05. So let's go ahead and do this. We want to go to the 1mu sheet, and we are doing a left tail test because the alternate hypothesis was that it was less than 800. Put in your alpha level, which is 0.05, your claimed mean, which is 800, your X bar is 750, your sample standard deviation is 25, and the sample size N was 24. And we get our test statistic, our critical value, and our p-value in the decision right there to reject the null hypothesis. So this we would say at the 0.05 alpha level, I was able to show that the average cost of a vacation is significantly less than $800 per person, according to these statistics. On B, it says calculate a 95% confidence interval for this problem. So let's go ahead and do that. I tell you what, before I do that problem, let's say that we had a problem in here that said summarize this at the most significant alpha level. Well, looking at this p-value, it says 0, but really it's about 10 to the negative 30th or so in scientific notation. But that's going to be less than any standard alpha level that we would use, even 0.0001. It's going to be less than that. So we would reject this at any alpha level, to tell you the truth. So we could say even clear down to this low at the 0.00001 alpha level, I was able to show that the average cost of vacation is significantly less than $800. Okay, let's go ahead and go to B, 95% confidence interval. So we just go down to the 95 to the confidence interval area. We put in our information, our confidence level, our sample size, X bar, and our standard deviation, and we get our confidence interval right here, and we could say that I'm 95% sure that the average cost of a vacation is between $739.44 to $760.56 per person. C says how many more people would you need to sample to be within $3 of the true average vacation cost and still maintaining a 95% confidence level. So the confidence interval would be 95%. The margin of error would be $3, and our standard deviation was 25. That was given before on this problem, and we get a total sample size needed to be 267. Now it said how many more, so we would subtract off our 24 people that were already sampled, and we get 243 more people would need to be sampled. So let's go to problem 2. Problem 2 are some problems that you really need to think about without Excel. It says, is it possible that you could reject the null hypothesis when the point estimate was not equal to the null hypothesis? Yes, you could, because again we're saying, could you not reject the null hypothesis? Yeah, you could not reject the null hypothesis if we look at this. For example, if we have a situation going on where maybe the claim is that it's let's look at this one, for example. If the claim was 800, but my X bar was not equal to that claim, let's say 799, then I didn't reject the null hypothesis. It's not far enough away from the claim to reject it. So again, that's 2A. So could you not reject the null hypothesis when the point estimate was not equal to the null hypothesis? Yes. The point estimate for the hypothesis test for the mean is your x bar, and if your x bar is close enough to the claimed population mean mu, then it's possible that you may not reject the null hypothesis. Same way with percentages. If your sample percentage is close enough to the claimed percentage, you may not reject the null hypothesis. Okay, this is thinking about rejection here too. On part B it says if the test statistic was 1.4 and the null hypothesis was mu equals 36 and you got critical values of negative 1.96 and 1.96, would you reject the null hypothesis? Well, really the mu equals 36, we don't even need to know that. Here's the important thing. We have critical values of negative 1.96 and 1.96 that determine the rejection regions. This must be a two-tailed test. 1.4 does not fall into that rejection region, into either one of the rejection regions. It's not greater than 1.96 and it's not less than negative 1.96. And we can see that on the Excel sheet as well. On a two-tailed test, we have two rejection regions. And let's take a look at this. Let's say from negative 3 to 3 or so. You have two rejection regions, and if they are 1.96 and you got 1.4, it doesn't fall into the rejection region. C says if the test statistic is 1.8 and you have rejection regions of negative 1.65 and 1.65, would you reject the null hypothesis? Yes, you would, because the test statistic falls into the upper rejection region. Again, this must be a two-tailed test because there's two rejection regions. Okay, D says if your p-value is 0.001 and your alpha level is 0.05, would you reject? Yep, because if your p-value is less than your alpha, you reject the null hypothesis. If your test statistic is 1.8 and you got a critical value of 1.65, would you reject the null hypothesis? Yes, you would. This must be a right-tailed test because we have only one critical value and it's positive. This falls into that critical value region, that rejection region, because it's greater than 1.65. Let's take a look at F. If the test statistic is 1.8 and you got critical values of negative 1.65, would you reject the null hypothesis? No, this would be a left-tailed test, so you only have one critical value of negative 1.65, so if the test statistic is negative 1.65 or less, you would reject. But the test statistic is 1.8, so you would not reject the null hypothesis on that one. If your p-value is 0.0036, what would be the most significant alpha level? It would be 0.01, because you couldn't go any lower than 0.01 and still reject the null hypothesis. On this one, there would be no significant alpha level that you could reject the null hypothesis. So that would be no significant alpha level on that one. So let's go ahead to problem 3. Problem 3 says that Charles claims he makes 90% of his foul shots to the foul line. Coach thinks that Charles' claim is too high. So your null hypothesis here would be that P is greater than or equal to 90%. That comes right from the claim, that he makes at least 90%, and it's about percentages. So again, P is greater than or equal to 90%, making the alternate hypothesis P is less than 90%. So your so Charles shot 100 foul shots from the line and made 85 of them. Test the claim at the 0.01 alpha level. Your N is 100. Your X is 85. Number of success is 85, and we're testing at a 0.01 alpha level. So I'd go to the Excel sheet, go to the 1P sheet, and what we're doing here is a left-tailed test. So let's move over here a little bit. We'll put in the alpha level, which was 0.01, the claim percentage, which was 0.9, our sample size 100, and our number of successes 85, and we get this information here, and we see that we do not reject the null hypothesis. Okay, our p-value is not less than our alpha level. Now, what will we do at the 0.05 alpha level? Well, if we check the 0.05 alpha level, we would reject the null hypothesis because my p-value, 0.04, is less than my alpha level. Also, I can tell this because my test statistic is a little bit lower or inside the rejection region determined by my critical value, negative 1.64. So that's another way to tell if you reject your null hypothesis, if your test statistic is inside that rejection region. So it's less than negative 1.64, so we reject the null hypothesis. And again, on p-values, which was part D, it is 0.04. 0.04 is less than 0.05. Now, the most significant alpha level actually is 0.05, because if you try to drop it down to 0.01, you will not be able to reject the null hypothesis. So the most significant alpha level is 0.05. Now, part E says make a 99% confidence interval for this problem. So the confidence level is 99, sample size 100, number of successes is 85, and we get our confidence interval right here, and we could say that I am 99% sure that Charles shoots between 75.8% and 94.2 approximately percent at the foul line. Part F says how many more would you need to sample, how many more foul shots would Charles need to shoot to get his estimate down to 1%. So that's a sample size question. So your confidence level is 0.99, margin of error is 1%, that's given in problem 3F, 1%, and our point estimate, our estimate for P hat is 0.85 because he made 85 out of 100. We have a previous estimate, 85 out of 100, 0.85. Put that right there and we get 8,460. But again, the question was how many more would he have to shoot, so subtract the 100 he already did and we get 8,360. If we did not have a previous estimate, then he'd have to shoot 16,588 shots. And that is the second practice test.